To introduce Jonathan Weinberger, and he's going to give us a talk about directed univalence and the Yoneda embedding for synthetic infinity one categories.
Thanks, Peter. Thanks, everyone, for showing up. Hi, Valeria, and whoever else is online, Jose, I guess. Yeah, I'm going to talk about some joint work with Daniel Gratzer and Ulrich Buchholz, and also some joint work and formalization with Nikolai Kudasov and Emily Reel. Yeah, so roughly this talk will be about synthetic infinity categories, and let's see what those are about. So I feel like I have a slight reverb, so maybe this. So people should still be able to hear me, but I feel like probably should turn down the volume of this. Right.
Yeah, but if somebody wants to ask a question, you have to turn it up again. That's our.
Yeah, maybe they can. Maybe they can indicate in the chat or something.
Yeah, okay. And then
yeah. I think doing it on my computer is also not great because then it'll. Just be the same effect over and over again. Anyway, so thanks. So I want to start with this kind of programmatic quote, kind of working towards what I mean with synthetic here. So there's this kind of observation or kind of thesis by Yuri Manin from 2009 that basically speaks to the point that in the 21st century, kind of homotopical structures become more and more important compared to kind of rigid structures like sets. And in particular, they will play an increasingly foundational role. So he said that the kind of foundational role played by sets, which are these kind of clouds of discrete elements, we envisage some sorts of vague spaces that are that we really only think of up to deformation, right? So in this picture, we would kind of, straight up identify the torus with the coffee mug, and Manin speaks of this kind of ongoing reversal in the collective consciousness of mathematicians. The homotopical picture of the world becomes the basic intuition compared to the discrete one. So I'm not necessarily claiming that this is kind of true for all mathematics, but it's true for certain branches of mathematics, and it's true with kind of increasing importance, such as in particular kind of topology, but also geometry and even like computer science and mathematical physics. So one kind of program in which this has been carried out and made precise is this area called homotopy type theory, which is an alternative foundation system. So many people here have gotten some taste of this kind of last semester, and then I guess different talks at different venues. So just very roughly, in kind of standard set theory, we have sets as the basic notions, which are these kind of discrete collections of elements. But in homotopy type theory, we think of first of all, the basic notions are not called sets, they're called types. And more precisely, they can be described as homotopy types. So basically, these elementary objects are now topological spaces rather than kind of sets which are discrete topological spaces. So in particular, they will contain sets, but they will contain strictly more. And it's not just topological spaces, which usually are thought of as like a set theoretic concept somehow. But it's really kind of equivalence classes of those, which we can think of as homotopy types. And these homotopy types, the nice way is that like one single homotopy type, the nice thing is that we won't even have to take equivalence classes or something like that, but rather the notion of equality in that system will take care of that for us. So that's one way to see this. And And this is kind of a program that has been developed by various people. So it goes back to, I mean, it all builds on nothing topological, but like a constructive alternative foundation due to Martin Löf in the 1970s, called Martin Löf type theory. Who first introduced these kinds of identity types that we are interested in. Before thinking about any kind of topological meaning of those, it was just about having like logical, like a good logical way to talk about kind of Leibniz equality. And then in the 90s, and in particular the early 2000s, and ever since, people have thought about like topological interpretations and models of this theory. Very notably, I mean, there was the early work by Hofmann-Streicher, who observed that this notion of identity can be interpreted in the category of groupoids, and then a little bit later, both Wygotsky and Streicher suggested actually that you should be able to interpret this in a model of higher dimensional, infinite dimensional groupoids actually. Audi Warren came up with a very general semantics actually for these identity types and the type formers in the context of what's called model categories. So those are a way of doing abstract homotopy theory internally to a vast class of categories. So not just topological spaces, but kind of homological categories like chain complexes or I don't know, sheaf categories, things like that. And there's been a growing amount of work ever since. What's particularly, I mean, what this allows us to do is we can do homotopy theory in that setting. So we can analyze spaces by kind of their homotopical or homological invariance. And also importantly is that this language, homotopy type theory, is actually a programming language that literally has various implementations and libraries. So we can even formalize and have the computer verify that our proofs are correct. So just kind of one example to give you some intuition, like traditionally in analytic set theoretic foundations, the circle would be defined as like the set of points with distance exactly 1 from the origin. So you know, some point set. And then if we want to kind of compute the fundamental group of that, let's say, I mean, we have to, you have to work with that set theoretic model. Whereas in homotopy type theory, we introduce the circle really as a data type that is really generated by giving a point, the base point, and then giving a non-trivial self-identification of that point. And the freeness is kind of gives you a universal property of that object defined up to homotopy, because in that theory, all the equalities are really homotopies. So in particular, everything that we can write down is respected by homotopy equivalence. And it turns out you can do, the same computations that you can, like the computations that classically hold, very often also hold in those cases, modulo maybe some additional axioms that we would need. But what this allows us to do is it allows us to replay the classical theory in in like a synthetic way, first of all, and also in a much wider class of models. Okay, so now we might not just be interested in doing homotopy theory, but actually category theory, or in this context, what people call higher category theory. So, I mean, a category you can think of as something consisting of a set of objects, and such that you have arrows between those objects, and like a composition operation that behaves well. And an infinity category, at least for me in that talk, is just that same structure, but all interpreted with respect to like a homotopical ambient theory. So instead of a set of points, we have a space of points. And for each pair of points, we have a space of morphisms between them, and the composition operation is continuous, and then the laws of a category are all witnessed by homotopies. That's essentially what an infinity category is. So how might we express this in hot? Is there some chance in which we could hope to express this? Well, the problem is that in hot we have these path types, A equals B. So when I write A equals B, that's not necessarily a proposition, it's a full space of identifications. Right, so you can have, I mean, non-trivial loop spaces. So even if you look at a path type such as A equals to A, like in topology, that's, can turn out to be very complicated. So the way that these path types are introduced is in such a way that they actually are supposed to model an equivalence relation. So that means in particular, this notion of equality is symmetric. So that means it can't be used, at least not directly, to model arrow types, because those should not be symmetric. So there are several ways around this investigated by several people, kind of some in like a type theoretic setting, others in different synthetic but not type theoretic settings. And in our work, what we're using is an extended version of homotopy type theory called simplicial type theory. This goes back to Real Schulman from 2017, and our work is also very much inspired by some other work that I mentioned here, including the work by Emily Real and Don Verity on what they call infinity cosmos theory, and some recent work of Szynski and collaborators on kind of synthetic higher category theory, and also Martini Wolf's recent work on kind of internal infinity topos theory. Yeah, I mean, these are all kind of very technical terms, but what I want to highlight is that what we are working on is really like a formal language, which is, I mean, something that, that just isn't the case for some of these theories that I'm mentioning here. Really like a formal constructive language. So we start from just standard homotopy type theory, which is like a synthetic version of homotopy theory. So topological spaces up to homotopy. And then what we're doing is we're adding an interval to it. So a type delta 1 that is, contains of 2 points and then an arrow going from one to the other. More precisely, we're really adding the Levier theory of this interval to the theory. So we're looking at all the powers, but then we also allow ourselves to look at retracts. So like subcomplexes of these n cubes, and those give us the n simplices and further subobjects of those. So the reason behind this is we want to model composition in a coherent way. So that means we have to introduce certain shapes to accommodate for, what does it mean to be an arrow? What does it mean to compose two arrows? So doing kind of that all on the homotopy type theoretical level would give us a lot of information. It would give us a lot of homotopies to carry around to take care of all the time. So there's this gadget called extension type that is added on top of this. So the idea is if we have a type family P over a shape psi, and we have some subshape phi of psi, and we have some section on the smaller piece called phi, then we want to be able to talk about all the sections B, so all the dependent functions B that are strict extensions of this A. So if I were just interested in extensions up to homotopy, then I would not need to introduce kind of this machinery. But since I'm interested in actually strict sections, I just have to introduce this via a new type former, because otherwise there's this notion of weak equality that I've talked about, which basically is like homotopy. But then there's also a notion of strict equality or judgmental equality, which is a judgment and it's not reified as a type. So that's why we need to have these types. So the categorical semantics, it's just given by a pullback or a pullback in the fiber if we're in the dependent case. But the important thing is, so in the model, it's not hard to show that these exist in the appropriate cases. But the point is that we're really adding this to the syntax, not just as sugar, but really as a new type former. So it's maybe best to see kind of how this works in practice. With this, we can define Hom types by saying, I have a type B and two terms A, B. And then the type of homomorphisms should be all the arrows from the interval into B that restrict appropriately on the boundary.
Sorry, John, stop a minute, if you can. I mean,
so that, well, that's what this type over here does. And then I can also look at like a dependent version of this where I have an arrow in the fiber or I have an arrow in the base, and then I can look at an arrow kind of lying over that arrow that passes through the fibers of the family. So the corresponding picture here would be, yeah, I don't, from this angle, I can't tell if the color scheme
It's okay.
is good, but yeah, this keeps changing from screen to screen. Let's say if I have an arrow W in like the base type and I have a type family P over that base type, so this can be equivalently kind of bundled together into one like total type, like a total space of a fibration in topology. And I can look at all the arrows that lie over here, maybe fixing these endpoints or not. Yeah.
P tilde, this is just P.
It's the sigma. Well, it's the, so I mean it's this thing where I can either look at a type family P from B to U, or I can look at a map. I mean, this corresponds to looking at the total sigma type, that family, which projects down to B. This is like the type theoretical version of this correspondence between kind of in the index spaces and fibrations. And I can do this also for like other shapes. So I can look at kind of two simplices in the base and then two simplices lying over, or like a two simplex in the base and then only like this upper part of two composable arrows lying over, or things like that. So this is a lot of flexibility that I can do here. So now we want to use this to define infinity categories in that setting. And the way to do this, first of all, we need to say that we have composition. And this is done by saying that a type has composition if it satisfies this Siegel condition, meaning that it perceives this pair of two anonymous composable arrows as being equivalent to the full tube simplex, which is, you know, a field of arrows whose inner part is filled, meaning that this is a diagram that actually comes. This is expressed by this first condition. So moreover, this really is a homotopy invariant condition because it says that a certain map, like the map that we kind of in the reverse direction get from restricting any diagram like this to just this shape, you know, this part of the boundary is an equivalence. So then there is this kind of, this is almost like a category, but there's this kind of mismatch that we have two potential notions of isomorphism. First of all, we have the path type or the identity types, which are just there for every type whatsoever. But then we also, from the Hom type, can define a type of isomorphisms, which is just defined to be morphisms that have like inverses on both sides. And there is a canonical comparison map that maps like the reflexivity of a point to like the constant map at that point. And requiring this to be an equivalence means that these two possible notions of isomorphism are the same. So if these two conditions are satisfied simultaneously for a given type, then that's what I want to call a category. Okay. Yeah, and then, well, I could also just look at the comparison that maps like a reflexivity term to, again, just the identity at that term. So the point is, I mean, here on the left-hand side, these reflexivity terms are just introduced. I mean, they're given by the rules of the type former as these reflex terms. And the terms in the Hom type or the isotype are just given by the constant term, kind of int x is defined as lambda I dot lambda a dot x. So the constant map, the constant map that gives me x. And I can look at the comparison just to the, just with that map as a homomorphism, not as an isomorphism, and then asking that this be an equivalence gives me what the notion of groupoid or infinity groupoid in that context is. And I mean, moreover, this implies that every arrow is invertible because now the type of just homomorphisms, in particular will, you'll always get an inverse because they're equivalent to paths and paths always have an inverse. So I've kind of motivated this intuitively, but actually, due to the work of various people, one can show that this gives, an adequate internalization of the of infinity categories. So we can say synthetic infinity category theory in that case, in that sense, interprets to ordinary infinity category theory, and actually, at least in part, we know that it interprets into internal infinity category theory because these models here are not just going to be infinity category of infinity categories, but they will also include internal infinity categories in a given infinity topos, which is like, one way of doing the higher version of internal category theory. So what's interesting about this is usually categories are defined, as some kind of structure, right? So a category consists of a set of objects and then kind of a family of morphisms parameterized over that, such that blah, blah, blah. But here I've said, okay, I call a type a category if it satisfies a certain set of two properties. What's also interesting is that it's only two properties where I'm talking about the composition conditions. If you formulate them in set theoretic foundations, you get an infinite tower of composition conditions of composition data together with coherences between them. So this is kind of another maybe miracle if you see it for the first time. But this has to do with kind of the power of all of these conditions being internal data. So first of all, any type here now doesn't interpret just as a space, but actually a simplicial space. So the semantics of this is like a given type externally will correspond to something like a diagram on the simplex category into like the category of the higher category of spaces. So any type in itself will already have will come with kind of data of simplices in n dimensions for all n. And then somehow, because these composition conditions, or this composition condition here is formulated internally with respect to the exponential, it unfolds to an infinite set of conditions in the set theoretic model. So this is a very easy, and in particular, it's really a finite definition. Like this only speaks of composition data up to including dimension 2, but it unfolds into composition data in all dimensions with no highest level of truncation. And in particular, it's only a proposition. I mean, it's not structure all of a sudden. So being a category now is actually being a category. It's a proposition. It's not structure that is a category. And it's in similar ways you can kind of do higher group theory here, which is also kind of interesting. But what this kind of gives us as a consequence is that we get a lot of kind of the expected properties for free. So note also in that definition, I didn't say that composition had to be associative, because that's actually something that you can prove just from that definition. And you can prove a bunch of other properties. So yeah, so associativity and unitality, you can prove any map between two categories will automatically be a functor. You can define the type of natural transformations as the type of homomorphisms in the functor type or the functor category. And this will automatically kind of unfold to the right definition of natural transformation that you would expect. These families of naturality squares. And that's kind of nice. So you get a lot of kind of naturality properties for free. So what we're particularly interested in is kind of functorial type families, meaning that if I have, so in kind of homotopy type theory, any family has the property that if we have a path in the base, then this induces a path transport map between the fibers. So just like a fibration traditionally in homotopy theory should. We can ask now the same thing about categories, which naturally leads us to this concept of kind of fibered categories. And that's a theory which I have developed further as part of my PhD thesis and joint work with Ulrich Buchholz. Kind of one category theory, these are called Grothendieck fibrations or fibered categories. So here one talks about co-Cartesian or Cartesian fibrations. And there was preliminary work on this by Riehl and Schulman in their paper, but there the fibers were supposed to be groupoids rather than general categories. So we extended this to categories. And this includes the development of a fibered Yoneda lemma, or respectively a generalized co-Cartesian version of this, where we're kind of comparing the type of sections in a family with the fiber at the canonical element, in this case, the identity. I'm gonna, so this is, yeah. So in the kind of earlier picture, the discrete picture, where the fibers were supposed to be groupoids, the corresponding notion of fibration is called covariant family. It has many other names in the more traditional literature. So often they're called left fibrations. And they can be defined by an arrow lifting property, where we're saying the type family C over A is covariant if for every arrow U in the base and for every X in the fiber over the initial point of that arrow, the starting point of that arrow, up to homotopy, there is a unique way to lift that arrow in the base to the arrow, to an arrow in the fiber lying over that arrow. So in other ways, we have like arrow transport in one direction, in the forward direction. And of course, there's a dual version, which would give you like a contravariant action in the backward direction. And those fibrations, I mean, traditionally, they're called like discrete fibrations or discrete up fibrations, and they correspond to presheaves. So kind of this setting is very nice to, we can't quite talk about presheaves yet, but we can talk about the fibration version of those. So this is what Will Schulman kind of developed in the paper that they wrote about this as like one of the first interesting topics to explore. And well, they were able to prove that these have all the, this notion gives rise, this notion is well behaved. We have kind of path lifting that coheres in the right way and behaves natural with respect to kind of fibered maps. And in particular, I mean, what should be an example of such a fibration? Well, if they correspond to presheaves or covariant presheaves, then the example should be kind of the Hom functor, where the Hom functor in one variable, depending on the variance you want. So in this case, the Hom A blank is a covariant family, something that they proved. And one of the important consequences of this is exactly this, like Yoneda lemma that I mentioned, which also, in particular for those people who were here last semester for the hot seminar, this can be viewed as like a directed generalization of the path induction principle. So I don't have time to really get into this, but that's something that they proved. With Ulrich, we later generalized this to the co-Cartesian case. But in particular, not too long ago, with Emily and Nikolai, we've actually gave a formalization of this result for the discrete case in a new proof assistant developed by Nikolai. And what's interesting here is, this is really a far-reaching generalization of the one categorical Yoneda lemma, but our synthetic, or our version of, the initial proof by real Schulman, for this synthetic infinity case is easier than the one in the one categorical case, even though that statement is much stronger than the one in the one categorical case. So how can that be? Well, this speaks to the point of this programming, this kind of alternative foundation system, because we just get a lot of naturality properties for free. Like if you prove the one categorical Yoneda lemma, you have this like map in like from left to right, which is, you're evaluating at the identity at the canonical element, but then you have to produce somehow a map going in the other way. And this type here can be viewed as kind of natural transformations or like fiber maps. And the hard thing kind of is to show that your candidate map actually lands in that object. So actually defines a natural transformation. But here, we can just write it down. And you have to type check that, this term here, which is like the forward action of this covariant family, that this actually, you have to show that this actually kind of, type checks and actually lands in here, but this is like a very easy syntactic check. This is, basically just using lambda calculus together with like a special property there. So this is some snippet of code containing the definition of the Hom types in the RZK, or the RESC proof assistant, named after Charles Resk, who developed, was at the forefront of doing infinity category theory and infinity topos theory. This actually helped catch a kind of circular argument in the earlier version of the real Schulman paper. So that really, to us personally, showed the benefit of formalizing things. And we have a growing library of results that anyone is welcome to join or ask me about for this proof assistant. So this is really the first formalization and the first formalization project that actually didn't stop at, or didn't primarily aim for just giving the definition of infinity category theory, but actually giving, working results that you would want. Okay, so a bunch of things have been done. There's been various developments on kind of vibrations in that setting, limits and co-limits due to Cesar Bardomiano, and these formalizations that I mentioned, but many desiderata are still missing from that picture. So as I mentioned earlier, we cannot do presheaf theory properly in that case, or in that setting, because we don't even have like the infinity category of spaces. So when I say spaces, I really mean infinity groupoids. We don't have any non-trivial infinity categories to begin with. So, I mean, we have a bunch of kind of non-trivial one categories, like the simplex or something, but those are just one categories, one actual infinity categories that are not actually just one categories. And I mean, applications of infinity categories in particular include kind of higher dimensional version of algebra. So in higher algebra, people are dealing with things like higher groups or higher operands or these kinds of things. They deal with kind of derived schemes in like modern algebraic geometry. So all of these things, it's not really like this theory doesn't seem to be amenable to talk about them. So what can we do? Turns out that adding certain modal operators to that picture is what unlocks a bunch of new constructions. So to be able to do this, properly, one really has to think hard of a way to, first of all, extend type theory by a bunch of modalities that interact with each other, but that also will have to interact with the type theory, and moreover, it's a dependent type theory. So kind of having modalities in that dependent setting, even just one modality in this dependent setting, requires some serious work both on the syntactic and the semantic level. And luckily, this has been developed in like a different long program under the name of multimodal dependent type theory, to Daniel Gratzer and Alex Cabos, Andreas Neutz, Lars Birkedal, and in particular, Daniel Gratzer has done a lot of work on that ever since in his PhD thesis and other projects. And finally, kind of recently, we were able to merge this multimodal story with our simplicial setting. So one of the main constructions that we want to perform is we want to construct, the infinity categories of infinity categories, small infinity categories, or the infinity categories of small infinity groupoids. And these act as kind of structured universes, right? So we have this like big universe of all types, but a type in general here doesn't have a lot of structure, it doesn't have composition, we're not really interested in that, and the universe also doesn't have like the right structure. So we really want to kind of carve out all the types that are categories, but if we did that in the naive way, well, we would still get a type what this type wouldn't be a category because the type of morphisms is completely not controlled and just doesn't behave well. So to construct these envisioned types internally in the theory, there is some gadget that we can use if we take the interval and kind of forget that it's totally ordered, because then what happens is suddenly we're in a bigger category, not the category of simplicial objects like over here, but then we're in the category of cubical objects where like this shape category gets replaced by just the category of cubes. And here the interval has the special property that exponentiation with it does have a right adjoint. And this right adjoint is used, it's called sometimes the amazing right adjoint, and it kind of has had some uses in synthetic differential geometry because it kind of is also good to model the formal behavior of like an interval of infinitesimals if you want. But in 2018, this group of people, the Carter, Orton, Pitt, Spitters, have kind of exhibited the use of this tiny interval with the amazing right adjoint to define these kind of universal types that are somehow classifying for a certain notion of vibrations, and then could yield, our construction for let's just say for now the infinity category of groupoids or spaces. From now on, I'll just call them spaces. So first of all, we have to take our simplicial type theory and make it a little bit larger by forgetting some axiom, so that now we work in a version of cubical type theory, and then we're adding a bunch of other operators. So we're adding the opposite operator, where you can think of this as saying just the n simplices are reversed. So this corresponds to going from a category to its opposite category, right? Where you have arrows in the reverse direction. The core modality denoted by flat is the maximal subgroupoid of A. So you restrict your arrows only to the ones that are isomorphisms. And this has a right adjoint. It's supposed to have a right adjoint, and this is actually turns out to be true in the model, called sharp, which acts as code discretization. So one way to think about this, at least intuitively, is as a certain kind of localization. But I mean, what it means is that it kind of gives you freely, or maybe co-freely, an arrow. Like it gives you, for each pair of points, it gives you, one arrow from one to the other. It's like a directed version of the co-discrete topology, where this is a directed version of the discrete topology. And then we also need the twisted arrow type that you can imagine similar to the standard arrow type. But instead of, for instance, the morphisms being squares, I mean, in the arrow type, usually you have like the objects are arrows like this and morphisms are squares, but then the twisted arrows, in the twisted arrow category, what you're doing is you're twisting one direction. Like that. And this is going to be important. The twisted arrows are going to be important for basically the normal categorical version of the Yoneda lemma that is not type rational. Okay, so there are a bunch of axioms. So first of all, this kind of type theory, like the simplicial embedded in the cubical type theory, we're calling triangulated type theory, because the simplicial types, you can understand them as the types, like among the cubical types, the ones that are simplicial are the one that can be triangulated in some sense. So the axioms that we're adding here, I'm only going to mention some of them, is first of all, well, we have to start with like a set-based interval. Then we have a kind of path type, also reified as a modality that has this amazing right adjoint. So we also have reversal on the interval. So this is the axiom that we call, that we're calling as I detects discreteness. So kind of being discrete with respect to the discrete modality, it's the same as being local with respect to the interval. So both are like reasonable notions of being discrete, and we're asking them to be the same. Again, this is justified in the actual semantics that we're interested in. We also at some point need to ask the interval to have just two global points, because so far, I mean, that just wasn't included in the axiomatization. There's also this axiom that says cubes or simplices separate, which says that being an equivalence between types can be detected kind of in the way that you would externally do this by asking for all the induced maps on the spaces of n simplices being a family of equivalences. So this is one very typical axiom that, again, it's true in the set theoretic case, and it's actually used in kind of set theoretic versions of infinity categories. That is, of course, much further developed than this one. But in order to be able to employ this kind of argument, we have to introduce it as an axiom. unless someone comes along and solves the problem of infinite objects in homotopy type theory tomorrow, but I don't know how likely that is. So, and then we also need to have some axioms about the twisted arrows that basically give us like structure maps. So just like the arrow category, I mean, the twisted arrows should have like a projection, you know, down to the, you know, down to A once, you know, in contravariant in one variable and covariant in the other. And then there's an axiom basically saying, I mean, basically saying that, you know, the implicit simplices look like this, which again internalizes a very classical construction. Okay, and another interesting axiom that goes back to Ingo Blechschmidt and his thesis on like doing algebraic geometry internally to toposes. So all just one-dimensional, just kind of classical Grothendieck, nothing derived algebraic geometry in one toposis. So he suggested this duality axiom that is also reminiscent to Car-Clavier type axioms from synthetic differential geometry, which says that finitely presented algebras are like can be equivalently seen by kind of mapping from the maps from the spectrum. Yeah, so this, if I were to talk about this properly, this could get kind of technical, but so let me skip over this. But the upshot here is that I've introduced some structures like this multimodal extension together with some axioms. And the first thing to do is, okay, we want to construct a universe of like the types that we're interested in. So for today, this won't be the category of categories, but it will be the category of spaces or, you know, groupoids all in the higher case. And kind of having this amazing right adjoint that I'm writing with, you know, index I, and this allows us to kind of define a derived predicate from this covariant family predicate that suddenly now gives us the right predicate to define our type classifying the left discrete fibrations. And since they're discrete, that means the fibers are groupoids. So that means the points of this universe are going to be groupoids. And so this goes back to this construction by Licata et al. That I mentioned earlier, but it's actually a kind of tweak of that construction due to Mitchell Riley from last year, who found a way to kind of further strengthen this result in some way by using this tiny object. And all of a sudden, we now can define our universe of spaces as like a simple sigma type. So this sigma here, it's just a primitive operator in the type theory. And this predicate, which is not primitive at all, but you know, is definable now, that gives us a candidate for the universe of spaces, and we can actually show that it is, you know, that its terms are groupoids or spaces. It is actually a category. It classifies the right kind of vibrations. Essentially, it is closed under the expected type formers, and it satisfies the directed version of the univalence axiom, meaning that the geometric arrows in that universe correspond to functors between the groupoids. Yeah, it's kind of interesting to see how this all goes, because it relies on a central theorem called the equivalence lemma or equivalence theorem, which says that assume we have a natural transformation between kind of left vibrations over the interval, then this family is natural isomorphism, if and only if it's a natural isomorphism at like both ends. So somehow from this square being a square where like everything is in equivalence, we only need to know this at like these ends. And to prove that, like this is one instance where we, for instance, need this axiom that we can detect equivalences on representables. And this also generalizes not just to squares, I mean to like squares and maps on the one simplex, but also to higher simplices. And in fact, that's what we also need to prove further theorems about that universe. So roughly, how does the construction go? Well, there's a canonical map to go from the geometric arrows to the functors. And that's basically given by evaluation of this family in spaces, and then just taking the covariant transport, which goes from like one fiber to the other. Okay, that's always a functor. Well, it's always a map, and those are groupoids, so it's always a functor. But how do we go in the other direction? So this is done via like a version of the mapping cone construction, also very much known in kind of classical topology and homotopy theory. So here, this is a kind of family of these sigma types where we're taking the fiber to the exponent of the path type that I is equal to 0. So this definition basically is a continuous way of saying, well, I want to, if I is equal to 0, then this is the fiber, but then this whole sigma type is then just the total type of that map, so just A. And if I is 1, then this implication is definitely not true. So then the fiber here becomes terminal. And then it's the sigma type along B over the terminal object. So this is just B. So this gives a continuous map of producing a family into S that starts at A and ends in B. And then one can show that those are actually inverses to each other, and that's where we make use of this. That's where we make use of this equivalence lemma. And then to prove that we have composition, that's where we need the higher versions. So what are applications of this? Well, with those we can prove what's called directed structure identity principles. So, I mean, in type theory, it's kind of always easy to define a type that has objects of a certain kind, because you can use like sigma types. So if I want to define the type of groups, I can say, okay, take the sigma type over the universe of sets together with structure maps, together with some laws, blah, blah. But then we don't want our type just to have the right objects. It should have the right notion of isomorphism, and in this case, actually the right notion of morphism. So in the context of just hot and directed univalence, they're not really morphisms, they're only, identities. So we want to generalize this kind of standard univalent structure identity principle to the directed setting. And this is something that comes out of having the universe of spaces now. So we can prove that, for instance, for pointed spaces, which are a derived notion of spaces, we have the right notion of homomorphisms. So those are just maps, between from A to B that preserve the base point, or we can define, in this case, the set-based monoids in a similar way. And if you kind of unwind all of this, you also get just monoid homomorphisms. And kind of maybe a bit more interestingly, and really to the kind of applications that we're looking for, we can kind of do all these things in the higher algebraic setting. So like if we want to do infinity monoids or infinity groups, those are again simplicial objects of some kind. So certain internal presheaves. Since we have spaces and opposite categories, we can talk about presheaves, and then being an infinity monoid again can be actually just expressed as a certain property. This is kind of a standard way in just set-based higher algebra to encode this, but it carries over into our setting. And similarly with the groups as well. And for those, one can also show, those give actually categories, and the categories have the right notion of isomorphism or of morphism, not isomorphism. So is it okay if I take 3 more minutes? Okay. So the next kind of result that we want to do after we have given this universe construction and proved that it has the expected and good properties, we want to prove the classical, I mean, an infinity version of the classical, the categorical Yoneda lemma. So before, the Yoneda lemma could only be expressed not for presheaves, but kind of vibrations. But now we actually want to talk about like presheaves, so things that that are indexed in S. And the hard part in the infinity setting is really to construct the Yoneda phi functor, so here called phi, and to exhibit, that you actually get a functor that has the right naturality properties. Well, yeah, on top of just having a functor, actually, that this is kind of, sufficiently natural. So it reads as you would expect that it reads. So the harms from a representable or co-representable into the object are the evaluation of that object at the fiber. But to even construct that phi here, that's what we need these twisted arrows for. Have syntheses that are okay. And we can show that this twisted arrow projection is a left vibration. And that means since our universe classifies these left vibrations, we can construct such a bifunctor. So this is the part where we have to prove something. So the twisted arrows are just given to us by an axiom and like a set of rules as a modal operator. But then we have to also prove that, it actually gives rise to a vibration, which turns out we can do. And then it turns out that this is the right candidate from which we can also prove the Yoneda lemma. We can prove that the presheaves satisfy kind of categories of presheaves satisfy the expected properties. So the universal property is that the category of presheaves is the free co-completion of a category. So that we can also prove here. And we can also prove the descent theorem that is like very important in applications. Another thing that we have like recently developed in that setting is the first steps in the theory of Kahn extensions. So Kahn extensions are a universal way of kind of unifying limits, co-limits, and other categorical constructions. But they're also kind of heavily used in the homotopy theory of categories. So we were able to prove some basic results on cofinal functors, and with that, give a nice, in my opinion, synthetic proof of what's called Quillen's theorem A. So that's a characterization of these right cofinal functors in terms of weak contractibility of a certain kind of fiber or comma object. And an application of this is that one can show that co-Cartesian vibrations satisfy a certain property known as properness or smoothness in the dual case for Cartesian vibrations. And here we've found actually proof in that setting that hasn't been known to us previously. So, I mean, all of this makes kind of sense also just for one categories, but kind of one categories, maybe within the model structure on categories. So kind of the homotopy theory of maybe just one categories, but it also can be, has been developed for infinity categories, but the proofs that we knew were all either, rather analytic at some point or not as slick as this one. So this proof basically, it's an application of this Quillen's theorem A, and it really uses the power of type theory because to prove this, we need to again, know that a certain fiber is weakly contractible so that it's kind of localization at the, like it's groupoidification. So the localization at the interval is contractible. And to prove this, one can do this in that setting in a very nice way by kind of, shuffling around sigma types and then using some of the synthetic theory of higher modalities as developed in particular by Reike, Schulman, and Spitters a couple of years ago, which is also like an overarching tool that is used a lot in our development and also in many developments in just kind of standard homotopy type theory. So there are a bunch of things that we're currently working on and planning to work on in the future, such as doing more higher algebra in that setting and actually doing, working on a construction of the infinity category of small infinity categories, and hopefully also extend our previous formalizations in, whatever system turns out to be amenable to that. So here's some of the references that go into the work, including the work itself. And with that, I'd like to thank everyone.
In this round. Are there any questions or comments?
Oh, yes, several questions here.
Okay,
Valeria,
please.
John, that was beautiful. Really very nice, starting from Manning to the end. Fantastic. I have two serious questions. Do you think you could go back to slide 30?
Sure.
Triangulated type theory,
Oh, okay.
I think.
This one or?
That one is good, but that was the second one that I wanted to go to. So the first one was a bit further, 30.
Well, yeah, it's kind of.
You can see on top, like, 25.
Oh, okay.
I'm
Yeah,
counting.
26, 25.
Okay, you said it.
You passed. Okay, 30, that's the one. So this is the most beautiful part, right? Because category theorists always, to me at least, because category theorists always wanted to have a sensible universe
That's right.
of spaces. And you have a proposal here, which I think is pretty good. Now, and it's using sigma types, and it's using simplicial.
That's right. I didn't explain this predicate is simp A. So that is the predicate that says that a cubical type is actually simplicial. So one way to say this is that it perceives every simplex to be, it perceives every cube to be totally ordered.
Every cube to be totally ordered.
Right, so if you try to map the cube into the two simplex, you have to squash it, right? Yeah. So otherwise, you have to degenerate it somehow.
Yeah.
In order to be simplicial, and So this predicate, it's kind of pretty easy to write down. And actually, there is some new work on this that expands a little bit on this like definition and kind of talks about localizations and also kind of other contexts. That was the last reference on my slide of references, but it got it overran. So I should fix that. But that's a grad student of Ulrich's who wrote a very nice paper that also kind of explains this a little bit more. But as you said, so we can just look at the at the type of those cubical types that are simplicial, and then just take another sigma where we somehow take all the types that are amazingly covariant families. And here what we really need is the amazing part, because if we just took is cof A there, this would just degenerate to just saying, oh, the type is a groupoid. But somehow this is cof A now can quantify over all the context. So it can detect, it can kind of lift in an appropriate way from saying something about a single type to saying something about all of its,
Excellent.
all of the general families over any context. And it turns out that we don't need to do anything more. We can actually prove, this is simplicial and this is a category which we hadn't at first, for some time we weren't sure, and we thought, oh, we have to kind of just apply the localization, which is like applying an internal sheaf operator, which we do have in that theory and in the model, so that's fine, but it just would make the type harder to work with. And somehow it's just much nicer that it actually works. And so kudos to Mitchell Riley, of whose toolbox this is really just an instance.
Very good, excellent. And now, can you go back to 22? Because now it's a comment, not a real question.
Yep.
Right. So, you're talking about multimodal dependent type theory, right? But I've been working on type theory, modal type theory. So remove the multi, remove the dependent since 1994, right? Mm-hmm. We were the first ones to kind of say, take modal logic and make it a type theory. So make it modal type theory. And then, what we do is different from what Grazia, Cavus, Newts, and Birkedau do, because they are only talking about box sorts of modalities. And okay, your amazing box, the twisted thing is completely crazy, very nice, but crazy in the sense of nice, but there's an awful lot of other things that one could do with diamonds, which do not happen on their sort of, the multi, we can do whatever kind of, there's an awful lot of elbow room for the multi part of the multi-model. But the difference between boxes and diamonds is not there. It is kind of deeper on the structure, and it's kind of interesting to try to think about how the diamonds kind of behave, and they, I've done more than 6, perhaps 8 kind of workshops all about intuitionistic modal logics and intuitionistic dependent, intuitionistic type modal type theories. And there's an awful lot of work there that, maybe when you apply it to your kinds of spaces and kind of simplicial things could improve things. I don't know. This is completely stupid on my, I have no idea. For instance, I do not know if I could do the dependent diamond, but I did do it in 2016, the dependent box. So it's a brave new world of other possibilities that I don't think have been considered here. I may be wrong, because Mike Schumann kind of did say that he did quite a bit of this stuff.
Right, but non-dependently. So he and Dan Licata had this kind of work from roughly around, maybe it started in 2014 or even earlier. So Mike Schumann, Dan Licata, and actually Mitchell Riley as well worked on this kind of very general framework of like vibrational, like fibered framework for multimodal type theory, non-dependent, but including, substructural logic and these kinds of, this kind of direction. And I think at some point they just stopped developing this general framework further. And I'm not aware that they ever had a write-up. They certainly had a bunch of talks and maybe drafts that kind of looked at dependent versions of part of this. But this one write-up that they have that covers a large class of theories, it's non-dependent, right? Because their focus, was to include kind of linear type theories, other substructural type theories, which turned out to be so kind of syntax heavy and kind of hard to check, if you actually get something consistent, that they said, okay, let's do the non-dependent story first. But then even just lifting, the normal like DTT part of this to to the dependent, even just looking at the kind of like standard intuitionistic, you know, multimodal type theories, like for as a dependent version. As I said, they sketched some of this out, but then I think stopped at some point, and that's what then has been carried out by Daniel and colleagues. So that's the part of the story that I know. Yeah.
Okay. I mean, I think it needs kind of digging deeper. It's not clear to me that they've done what I want to have done, but
I hear what you're saying, and I'm always happy to chat more, as you know.
Sure.
Yeah. And thank you. Yeah.
No, thank you. That's was really very good. I think the level of the trying to make sure that one could see why you're doing things the way you were kind of seemed very good to me. Thank you.
Thank you, Valeria.
Can you send me the slides and I can put them on the webpage?
Sure. Sure. Yeah.
Video later.
Yeah.
You mentioned an infinite tower of composition condition talk. It may get into too much detail, but I'm curious about that. How do you get this hierarchy? What's the base step?
So, okay, so what you want is, so what you will, so if you look at, can you see from behind there? Well, the camera.
Oh, okay.
Okay, so the idea is we start with an X, which is a diagram like this. There's like multiple ways to express this. Another one is via what's called the spine. So like the N spine is the chain of N. It's like the free chain of N composable arrows. So this is like, you know, we have like N arrows, chain of N arrows composable like that. And we want to say that yeah, so we want to say that like that X is local with respect to the inclusion of the N spine into delta N. So being local means whenever we have such a chain, we can complete it uniquely as a, you know, to like a composition N simplex. So if this is kind of hard to imagine, you can at first just look at this for, you know, N equals 2, and then you get exactly this condition here. So I mean, this is also an instance of like this condition for N equals 2. And so kind of what this unfolds to is to have equivalence, like a family of equivalences like this, where N simplices in X are equivalent to these N, so like the exponential of X to the spine, which we can then unravel to be like an iterated pullback of like arrows in X that are composable. So it would become conditions like this, you know, which is an infinite, I mean, it's an infinite collection. If you view all this, I mean, if you view at this, if you just look at this kind of syntactically, I mean, this is, you know, this all of this should be true for all, you know, for all N. So yeah.
So the levels are the discrete values of N.
The dimensions in which we have composition data.
I was wondering, the directed univalence is automatically satisfied in the synthetic. It's not an axiom that you assume.
That, yeah, it's a result. So I don't know what you mean by automatic now,
No,
but
it's a result.
It's a result.
Something that you
Yeah,
have to
we were
show.
able to prove. Yeah.
Yes. And does it do somehow to ordinary univalence in the core? Or
No.
no?
It certainly uses, I mean, we're assuming, so I mean, in this setting, we're just freely using univalence for every level of the universe of all types, which is actually like the original real Schulman type theory actually doesn't even use univalence. It uses function extensionality, but it doesn't use univalence. But I mean, if you have univalence, you can do like this conversion between the type of families and the type of just maps into the base. So I mean, it just allows you to, I mean, if you since the models are intended to be something like, pre-sheaves in infinity toposes, and infinity toposes are known to have univalent universes, I personally am fine with just using that freely. So I don't quite know how it would look like if you didn't have that, but it certainly is not I don't think it's not accurate to view it as just like a corollary. It's more, yeah. But also in particular to be able to prove that, we found that we needed to introduce other axioms. So I'm putting quotation marks because I can't give you like a counter model or something, but it's this case where you're trying to show something in a theory, and you just don't see any other way of proving something, and then you're just adding an axiom and kind of try to add axioms in such a way that you can justify them to be called a first principle with respect to like this domain specific language that you're looking at. So yeah, and so that's what these axioms are for us. And there has been earlier work that I didn't mention explicitly. I mean, it was on the slides, but I didn't mention explicitly in the talk. So there's work by Weaver and Licata from around 5-6 years ago, who worked not in simplicial, but in like a bicubical type theory where you have two axes of cubes. So one kind of categorical one and one like homotopical type theoretic one, where they were also able to construct such a universe of discrete vibrations and prove that it's a universe, and that prove that it's a category, and that it satisfies directed univalence. But for instance, they had this equivalence lemma, and if I'm not completely mistaken, I think it was an axiom for them rather. And so we were happy to actually have found some other axioms that just seemed kind of more elementary to us, to be able to prove that axiom. But it was also interesting, their methodology that they used to kind of complete this proof of directed univalence, because like one direction of the inverse is kind of the hard direction, and this prompted them to introduce another modality called, basically to do a kind of co-bar resolution of types, which certainly is also interesting, but yeah, somehow we didn't end up needing that modality, which I'm happy about, because somehow we could, like, a lot of these proofs that go into this are really just kind of lattice theory and looking at like normal forms of polynomials over like I algebras, and so that's kind of interesting, I think.
On a quote at the beginning and the whole sort of univalence point of view, This is probably the wrong group of people except Ben to talk to about this, but this raises some philosophical questions. Pretty profound, it seems. Right, because if you really mean that a donut is the same thing as a coffee mug, then you and I need to talk.
Well, in part it is.
I think, you know what I mean? There's something sort of radically platonic about this point of view, I think. There's something about it. We all agree there's something about the shape of a coffee mug that's the same as the shape of a donut. But to say that they are the same is the same in what way? So what is it that is the same? There is something. There's some archetype to which they both refer.
Right.
They are both instances of. Right. And that's a pretty radical thing to say, it seems to me. And I'm not saying it's wrong, I just think it's pretty radical.
Thanks. So, I mean, for me, this was my tongue-in-cheek way of giving an elevator pitch of just saying what univalence is supposed to have as a consequence. So I personally don't have a take on how exactly this forces you to be a Platonist, but I mean, suffice it to say that I'm not trying to make the point that all of mathematics, it just refers to certain branches of math and then DSLs that you are kind of can be concerned with. But the way in which, from the point of view of Hutt, they are the same is there are homotopy equivalences between them, and as per univalence, that means it's the same as having a propositional equality between them, and propositional equality is what is the notion of equality, and I mean it's the internal notion of equality in our theory, you know.
Yeah, I'm not claiming that I know what I'm talking about exactly. I'm just saying that there is something to investigate.
Yeah, I mean, there's
about mathematical objects. What are they? And if you take it seriously, then the objects are even more abstract than we used to think they were.
I mean, so yeah, so.
But for your point of view, your investigations, they're actually pretty concrete things, because they're terms in types, and there's syntax, and there's normal forms and algorithms and the rest. So,
well, okay. So about the kind of latter, since we have axioms in the theory, of course, the system doesn't have canonicity. So that speaks to like Weaver and Licata's work, who wanted to base it on cubicle type theory rather than Burckhardt, because in cubicle type theory you can prove the univalence axiom.
right.
So, I mean, this hasn't been exactly written down in that context, but if you took away the axioms and just look at like Plischl or cubicle type theory with extension types and with these multimodalities, so there are proofs for not that exact same system, but a similar system, and there's kind of a draft that I did with colleagues a while ago for these kind of extension types from Plischl type theory that you know, if you forget about the axioms, then you get a theory that admits normalization, and this can actually in itself be done in an internal way, internally to a gluing topos that has like two modalities that kind of give you the semantic part and the syntactic part of the object, allowing you to do a synthetic version of Tate computability. and normalization by evaluation. So this has been developed by Carlo Angioli and John Sterling in his PhD thesis, and then later extended to kind of multimodal type theory, but also kind of cubical multimodal type theory by Daniel Gretzer and some colleagues in some capacity, I believe. And you know, in that sense, it's the fragment that doesn't have axioms. It's probably safe to say that it has canonicity.
But John,
since we have the axioms, I mean, and since we have univalence, it's not like at face value, it's not going to be, computational in that sense.
Yeah, no, I didn't mean it. Yeah.
But a question there, John, because it doesn't. I mean, the way I understood it, you're starting from the point of view of simplicial types, and kind of the homotopy type theory was kind of built in from the beginning. So you kind of you built in the triangulated type theory, kind of. It's the same thing that I keep saying about the groupoid model. Kind of, it was about having the simplest case that one could possibly have of the calculus of constructions, right? So, and it was a very good model because it showed lots of other things.
Yes.
But it's not supposed to be the only model of calculus.
No, that's right. So
and here the same thing happens, right? We're kind of saying, let's kind of think about these things like the cup and the donut in terms of simplicial sets somehow, kind of, to begin with.
Sorry, Drew was.
Well, I was going to say, Valeria, I think that's the point of the synthetic project is exactly that, right? That you don't want to say that you have one model. You want to build this axiomatically, synthetically.
That's right. So, I mean, I should say somewhere along the way, when adding these axioms, I am not sure I'm not sure that we don't maybe kind of like decrease the class of models. I mean, in the beginning, like if you just look at the kind of standard versions of simplicial homotopy type theory, you can show basically using Mike Schulman's strictification construction for universe and arbitrary infinity toposes that this interprets the internal infinity categories in infinity topos, but then kind of some of these axioms that I mentioned, I'm not sure I want to claim right now that they still hold in that generality. However, all of those can be justified within just the standard model, simplicial objects in spaces. And already that's all, already that is like an advancement, because the problem in constructing these, things like infinity categories, like the way that this is done in the classical analytical literature, it's hopelessly set-based, or, it can maybe do it in type theory, but then it would have to be, either try to formalize Lurie's higher topos theory, in lean, or work in like a two-level type theory, which is kind of tantamount, it's like a type theoretic version of model category, but where you also have non-fibrant types. So one could think about these things, but I mean, those maybe would be kind of type theoretic, but they wouldn't be synthetic in that sense. I mean, it would just, I'm not saying it's not a worthwhile project, but it would just not be synthetic in that sense. And another thing about this Licata-Weaver direction, so they had in mind also, I think, some kind of more computer science point of view, where hopefully we can run all this by kind of rebasing it with like a cubical type theory, which is known to have, computational meaning.
Right.
But the kind of cubical models, I mean, from the point of like homotopy theory and higher category theory, the cubical models of infinity categories aren't that well understood, and there's still, I mean, there has been progress, but there are also still questions about kind of the model structures on cubical sets, like which one correspond to the classical model structure of spaces or not. And so
I mean, there was a reason that homotopy theory did not evolve along cubical lines.
Right. So, so for me personally, my main motivation for like driving this project further and further was to say, okay, I wanted to have a type theory that at least is kind of sufficiently synthetic, which of course is subjective to some extent at the end of the day, or maybe completely subjective, but in any case, that would be kind of, sufficiently synthetic, and that would actually interpret that, I mean, that would be kind of adequate in the semantical sense, meaning, our internal definition of infinity category corresponds to the correct external definition, and not just looks like something that, okay, maybe you can call it that internally, but then you don't really know externally what it corresponds to. But I agree, I mean, just like people did for cubical kind of models, and some person, Walter Sticklenberg, did like way back when, you could start thinking about realizability models of maybe some version of that theory, for instance, if maybe that's also what you were thinking of. I mean, that that could also be very worthwhile and very interesting. Sorry, Drew.
No, that was an interesting comment.
I mean, this was prompted by Valeria's comment. But,
No, thank you.
Okay.
I liked your answer. It makes lots of sense to me, at least. Not that I know anything about it, but kind of seems sensible. Thank you.
Yeah.
Thank you.
Thank you, everybody, for joining. And there will be time to talk more about this. We're going to post the slides. And on Friday, we have a talk by Soren at 4 p.m. in the MPP seminar, but it's also a GALAI talk. So I just wanted to mention that. Thank you very much.
Thank you.
Thanks a lot.
Thanks.
Thanks.